She said, no, your process takes another 10 minutes more, so I can't do it. It is already a 6-hour process. She says, well, if you add another 10 minutes, then I have to buy another 2 tools. My capacity just simply won't match up. And that becomes a bottleneck. I went back and I re-engineered the whole process to make it come exactly 6 hours. But that manufacturing issues being more real world versus research and development got a little tempered. Knowing what does not work for a specific application was worth as much as knowing what works.
Do you think that it's been time dependent on why Sematech had a bigger impact than what we've seen today with the public-private partnerships? Hey, Raj, thanks so much for joining us here on Micro Journeys. It's a pleasure for you to drive over here to Sacramento and join us on the podcast.
Thank you for having me here. And it's actually a pleasure for me to drive up here because we keep talking every week or every other week, and I never really got to see your office and to see you in person for a long time now. So,
yeah,
pleasure.
It's good to have you here, and you kind of see what happens behind the scenes a little bit. Mm-hmm. And speaking of behind the scenes, you have quite an interesting story. Your background, how built off of your education and created this illustrious career, and were born and raised over in India, mm-hmm. and you started your education over there, right? What got you into kind of the field of electronics? Was it a passion that you had? Was it something that you kind of found yourself falling in love with while you were in school? Why don't you describe that a little bit?
Illustrious, I don't know. But having said that, I think, I could never keep a toy intact when I was young. My father would get me a toy or my mom would get me a toy and I'd just break it apart. I always wanted to see what is inside, what made it work, what was it. But just besides that curiosity, I think somewhere in high school, I had a lot of good role models. And that's when I started recognizing the value of these role models. For example, one of my teachers, she was always pushing me towards science and tech and trying to understand things. I really, Kea Suma, her name was, she was amazing. And so she really, little by little, she would kind of tweak and then kindle my interest in that area. And there were also people like my father's friend who was an engineer at an aeronautics lab in India. But this guy was amazing. I mean, he was an engineer, but he would repair his car. He would repair his, stereo system. And he could stitch a suit. He could go and fix anything that was around. At the same time, he could cook up a phenomenal meal for many people. So I looked at this man and said, this man can do everything. And he was kind of an inspiration. I said, wow, this is something. So that journey kind of pushed me towards becoming an engineer like him. That kind of made my curiosity go high. And I said, well, if he can do it, I should be able to do it. So I started tearing apart things at home, like radios and tape decks and things like this. Soon enough, I became the local guy who could fix, VCRs and radios and things like this. So all our neighbors would come and drop these things off, and most of the time it would be like, there was a resistor that was burnt out, or there was some capacitor that just burnt out, and you could read the thing off and you knew what it was and replace it, and boom, you're back in business. So your reputation starts growing. I thought of myself as a hotshot electrical guy. Now electrical engineer who could go fix all this. So
everything's breaking around town. Let me take it to Raj. Raj
let's
knows
take it to
what
Raj.
to do. Yeah.
At least the street. So that was the fun part. And then there were things I couldn't fix. So I had to give it back to them. But all this kind of propelled me towards engineering. And eventually I said, I've got to do engineering. And that's how I ended up doing that.
Yeah. Did you decide when you were getting your undergraduate that you were going to go after a PhD or the high level education, or was it something that naturally just kind of started evolving as you went through your coursework?
Right. That's a great question, and I have to again thank some mentors. As I was going through my engineering degree and in Bangalore University, one thing that happened in 1987, I think, was there was this big discovery of superconductors, high temperature superconductors. Hopefully, room temperature will come soon. But this came out of IBM Zurich, and I was really impressed with what was happening because I was just about figuring out. I was in second year engineering, I think. I was figuring out about resistance and the impact of resistance on our lives and what it does in many things like electrical power systems as well as our stereos and radios. So I said, wow, if we can really cut out the resistance, this would be incredible. You could do lots of things. But then what are we doing about this in India? I see Zurich working on it. It's IBM. So there's a lot of stuff going on in the US. What are we doing in India? So I said, well, the best place to go to would be Indian Institute of Science, which is the Harvard of India in some sense. And let's go there and find out. So I took a bus and went across the town and landed up on campus. But I had no idea where and who I should go and see. So I was walking by and I saw this materials research lab. I said, okay, these guys ought to know something. This is a new material. So I walked in there and said, okay, now who should I talk to? He said, Director, Materials Research Lab. Okay, he should know something. So I walked into his office, knocked on his door. I said, sir, I'd like to find a little bit more about the superconductors and what you're doing on this. He said, who are you? He said, I'm just a student in engineering at Bangalore University, but I thought you should be doing something in this interesting field that's coming up. I said, why did you get interested in this? I said, I was just reading articles in newspapers and magazines and thought this sounds interesting. So he was gracious enough to not just throw me out of the room and just say, don't waste my time. But he said, oh, it is remarkable that you took the initiative to come all the way across the town and ask me these questions. Let me introduce you to one of our faculty members here who's working on that. So he introduced me to one, Dr. Harshavardhan, who's now still in the US, and he's actually working on some of these materials. And sent me to his lab with him. And I spent the entire day with him there, just looking at what he was doing, what he was trying to study. And when I walked out, he said, look, can't pay you, but if you're interested, you can come and, dabble around with me here. So that kind of got me in the direction of superconductors and this whole concept of research, what a PhD really is, and, how you go about doing it. It's not just engineering, but how do you put engineering to practical uses, especially as you're trying to break new ground? So that caught my fancy. I said, okay, I think I ought to go and get a PhD at some point. So that started the journey.
How did that influence your move from India to the United States? Why not stay in India and go and get your master's, your PhD? Why come to the United States?
Right. No, it would have been fantastic to go and get a PhD from Indian Institute of Science. It's a premier institute and it's a great place. But then I asked myself, what would I do after? I would have to teach, and not many opportunities to practice that. So, and the second thing was, as I was dabbling with this in Dr. Harshavardhan's lab, it also became very clear to me that this whole thing eventually has applications in electronics in conjunction with semiconductors. Perhaps that's one area where there would be an interest. And then I started looking into semiconductors and what it actually means. It was just scratching the surface. So I said, okay, if I'm going to do this, then I have to go abroad, especially to US, where there's a lot of work going on in this area, and that would be the right place to study this. So ended up coming to US.
Rochester, then Northwestern, right? Northwestern's
right.
Where you got your PhD, and then from there, what was the relationship? Was there a relationship, I guess is a better question, with IBM at the time? Or how did that, connection end up happening?
Right. There was really no connection with IBM in the beginning. But when I was at Northwestern, I had the privilege of having a scholarship from Argonne National Lab. And as I was working at Argonne National Lab on my research topics and studying at Northwestern, I also had the good fortune of getting an internship at Hewlett-Packard right here in the Bay Area. So when I went to Hewlett-Packard and I was working with my mentor over there, Laura Mirkarimi and others, it became obvious to me that some of the work that is going on in this topic, on these superconductors and ferroelectric materials, IBM was one pioneering company. So when I finished, or when I was about to finish my PhD, IBM was on campus. They were interviewing people. And I said, okay, let me go talk to them and see what happens. And when I got an offer from them, I said, how can you refuse? IBM is iconic.
Yeah.
So despite there being other attractive opportunities, I said, I'm just going to go east, go to IBM. And so that's how I ended up in IBM.
Which IBM did you end up going?
I started in the what they call SRDC, Semiconductor Research and Development Center out in Fishkill. But I also was very active in TJ Watson because I chose to go to SRDC in the beginning. They said, where do you want to go? And I preferred to go to SRDC because I wanted to get my hands on fab tools and real wafers that were really doing things. Because I was doing a lot of research. Let's try to go do some actual development and closer to manufacturing because that's a different experience. So I started there, but I also managed people in TJ Watson Research Labs, I think in almost concurrently at that point in time. I was working with a lot of people in TJ Watson as well.
And you were doing quite a bit of interesting stuff there. If I remember, DRAM was one of the focus areas, and then high K was the other one, correct?
That's correct. Yeah, DRAM was where I started, and it was quite interesting because you get to see so many aspects of semiconductor manufacturing or fabrication, process technology development, design. All these issues I'd never even thought of, never even heard of. It was such a great training ground for me, and started with DRAM but moved to logic soon. And then in logic, we were working on high K metal gates. That was a key project for IBM. And that was centered in TJ Watson. So I moved to TJ Watson for that job, but we had people in Fishkill also who were working with us.
Let's describe a little bit, because some people may not track what a DRAM is, right? And how DRAM fits into the memory ecosystem. Could you describe that a little bit?
Absolutely. DRAM is dynamic random access memory. So anytime you have a computer, for example, you need to have a place where you're going to store your memory for the processor and recall it back and forth as you need to, right? So DRAM is that volatile memory where you put things and you try to get it back for the processor whenever it needs it, and it's fast. So you need to get that going back and forth. Now I'm just emphasizing that because it's in contrast to something called non-volatile memory, like the flash memory, little key fobs that we use. That you store something on it, it stays on it. Whereas in DRAM, it's a little different. And then there is another class of memory called SRAM, or static, essentially RAM, which is much faster. And this RAM is closer to the processor, and it is super fast so that the processor can actually do something and hold it in that SRAM so that it can recall it very quickly. So DRAM is in between the storage class memory versus the static RAM or SRAM, and therefore you actually dynamically store things in there and recall them, and that's where DRAMs come in. But the advantage of DRAM is that it is very dense, so you can store a lot of information in there. SRAMs are not that dense. You need 6 transistors typically to make an SRAM work, whereas in case of a DRAM, you have a transistor and a capacitor. So the transistor turns on, charges the capacitor, and that's how you store your bit. So that's the key difference between them.
And they're used, I mean, for all applications today. It's not something that has transitioned out. I mean, it's a core piece of electronics. And another core piece is what you're describing with logic, right? And so you transitioned over to the logic space while you were over in IBM. So you really kind of got a good mix of different types of microelectronic exposure while at IBM, right?
Right, absolutely. No, like I said before, it's a great training ground. I call it IBM Academy. And there are so many people I meet today everywhere who started their careers at IBM, and they learned so much, and we all share that common bond. Our blood is blue in that sense forever. But going back to DRAM and talking about DRAM, it's very interesting because it's actually a challenge. It's a masterpiece in engineering excellence to make DRAMs, because you continuously shrink these capacitors and you're continuously trying to make more and more happen in a much smaller square footage, if you will. And that is what essentially led to a lot of new breakthroughs in microelectronics, which are still practiced today. Things that started 20 years ago. We wouldn't really have many of the capabilities that we do in semiconductors without those breakthroughs. Something else that is equally interesting is that DRAM itself, and this is not probably well known, but if you look at a data center, a giant portion of the data center is DRAM. Yes, there are processors too, but more so DRAM.
Yeah, of course, because you have to be able to store.
Exactly. You've got to store chunks of data. So, yeah.
It's interesting because this cross-pollination of technologies that you're describing here at IBM sounds like it created a foundational piece for you for your next portion of your career, which was over at Sematech, right?
That's right.
So Sematech is quite a gem that the world had for quite some time. Why don't you describe a little bit of what Sematech was and then what your role there was?
I mean, Sematech started way before I joined Sematech. Semiconductor Manufacturing Technologies is the acronym. And I think it was an act of Congress that literally led DARPA to fund Sematech. And in addition to that, they also requested, or not requested, but the industry came together to say, we are going to put the other half of the money. I think it was 150 million, if I remember correctly, or something like that.
Sounds like a public-private partnership.
It was a public-private partnership, exactly. And this was also because the industry was struggling at that point in time, given the dominance of the Japanese semiconductor industry and how fast they were growing. So the US industry recognized that they needed to do something. And so that's how Sematech came into existence. Over the years, I think the whole concept of Sematech evolved. US industry recovered, they were doing much better. Japanese industry was also doing well, but they were going up and down. Then you saw the rise of other countries coming into existence. It was just about. So Sematech opened up to international participation at that point in time. And then they started tasking themselves with industry-wide problems. How would we move to 200 millimeters? How would we move to 300 millimeters? And then at some point in time, they were even dabbling with 450 millimeters. Questions around what kind of standards should we have in a fab? So these are things that everybody across the industry needed help with. And no one could do it by themselves and hope that everybody would just simply adopt it.
And for those listening, when he's talking about the millimeter sizes, those are the wafer sizes.
Correct.
In which semiconductors are manufactured.
Yes.
So those different varying sizes of wafers are characteristic not only to the volumes that are coming out, but also are heavily tied into the technologies that they're manufactured on. More legacy stuff would be on the smaller wafer size, where the state of the art would be more on the larger wafer size. Over at Sematech, describe a little bit of what your role there was.
So I joined Sematech to lead what they call the front end group, where a lot of the device work, materials, processes, work was being done, some metrology work as well as reliability studies. So how do you essentially get devices to come up, and what are the next generation device technologies that you would look at? And it was an exciting time. We had participation from pretty much everyone across the industry, and interestingly enough, we were looking at activities jointly with SRC during that time, Semiconductor Research Corporation, and we were also doing some joint work with IMEC at one point in time, where we were funding IMEC to do some work with us on high-K metal gates jointly, so that we would have faster outputs. But Sematech, that particular group at Sematech was where I started, and then later I took over as the VP of materials and emerging technologies across Sematech, and we were looking at all front end, we were looking at back end, some of the packaging concepts that we talk about now, 3D and hetero integration activities. We were precursors to some of those concepts were being explored, as well as metrology and other things.
It's funny how a lot of these conversations are starting to come full circle, right? The concept, which seems to be a hot topic right now, of public-private partnerships.
That's right.
Was really established with the Sematech-related engagement and the government's overall foundation for that facility. Talking about die stacking or 3D integration. How you guys were pioneering a lot of these types of things, which are now integrated into many different types of applications as a almost like a standard practice now.
It is. So. Absolutely. I mean, I go back and count my blessings on all the great people, inspiring people that I met throughout this journey. You learn from everyone, and as I interacted with them, whether they are engineers, whether they're technicians, or whoever they were, and every one of them had something interesting, something new that I could learn from, and many, many executives and how they think through their business propositions and what they should do or shouldn't do. And what was interesting about this time at Sematech was not only were we looking at some really cool, cutting edge concepts and ideas that we wanted to bring to life, but we also had to think, how would this really get manufactured eventually?
So it wasn't just a concept idea, because one of the downsides for a lot of R&D is that they get heavily focused on the benefits of the R&D without the forethought of how do I actually turn this into production. Right. So you guys were closing the loop on this.
We were trying to close the loop on it, but interesting. I'll tell you two anecdotes here. The first anecdote was I got indoctrinated in this thinking because when I was at IBM, I was a young engineer. I came up with something that had to be transferred worldwide to all the DRAM fabs that IBM had. Infineon, today Infineon, of course, those days it was Siemens. Siemens had its own fabs where we had to transfer this technology. They had to manufacture, and Toshiba. So I was talking to the engineer from Infineon, and she said, no, your process takes another 10 minutes more, so I can't do it. It is already a 6-hour process. And she said, no, I can't take it. I need it to be exactly 6 hours. That's what we are primed for. I said, what do you mean? She says, well, if you add another 10 minutes, then I have to buy another 2 tools.
Interesting.
And 2 more tools, because my capacity just simply won't match up. Because 10 minutes on a 6-hour process, I have today, she said something like 8 tools that are running. So if I add 10 minutes, then I can't run the same volume.
And if it's running 24 hours, that's 40 minutes a day.
Correct.
And then 40 minutes a day every single month.
Right.
Now you start expanding that out, and lo and behold, you're adding multiple days to the process that are aggregated over a period of time.
And that becomes a bottleneck. That particular process becomes a bottleneck. So therefore, she brought me to this reality check of, this is going to be a problem if you indeed decide that you're going to add 10 more minutes to this process. I went back and I re-engineered the whole process to make it come exactly 6 hours. But that manufacturing issues being more real world versus research and development, where we just simply go laissez-faire and just say, we're going to do whatever, is going to make this meet certain specs or certain new criteria, got a little tempered. So that is very interesting. And when I went to Sematech, and this exactly was a little more in play, because you would be looking at, let's say, 5 different options. You know that of these 5, 1 or 2 of them would be more optimal. And it may be dependent on the application space eventually. But knowing what does not work for a specific application was worth as much as knowing what works. Because public-private partnerships like Sematech don't really give a turnkey final solution. What they help their members and partners is letting them know what does not work and what is the direction to go at the end to match up with their specific product implementation.
Do you think that it's been time dependent on why Sematech had a bigger impact than what we've seen today with the public-private partnerships? And what I mean by that is during the time period, 80s, 90s, et cetera, for Sematech, the amount of influence that the government had in microelectronics was substantial, right? I mean, there was a lot more funding that would return back into applications there. Now we see a dominance of things like AI, we see 5G, you see a variety of these different industries that are influencing microelectronics, which kind of diminishes the role of the DARPAs, for example, of actually influencing a public-private partnership. Do you think that is still the case, or do you think there's a way of molding this?
It's a great question, but I tend to think a little differently in what's happening. I think the industry has evolved from that time. The role of the government is still the same. I think government does care about what happens in the country and how much are we manufacturing, what R&D is getting, is going to manufacturing in the country versus what's going out. But and the same thing goes for industries too. They have a role to play for their shareholders. But what has really changed over the years is, in the past, making the chip was a big thing. So there was a lot of research that was focused on getting the next generation chip technology in place. And that was being done by all the big companies that were making the chips. Move forward a little bit more, and what happened was, over the years, people recognized that, wait a minute, there is also a fabless segment of the market that is just designing the chips, and they were trying to get it made by somebody else. And so that started in a very rudimentary, small step manner, but it became more and more prevalent as a concept that was actually quite viable and profitable too, and useful. And then fast forward further, and what we saw was that the chip makers were having less and less of a role. While they were trying to do what they were supposed to do, they had more options in front of them. So they had to rely on the supplier community, the equipment suppliers and others, to do some of the research that they were doing before.
Interesting.
So in the past, it was that, the Intels and the IBMs and others were doing a lot of the materials research, a lot of the process research, some design concepts, everything. They were just trying to put all this together. Today, you'll see that a lot of the process research, materials research is being done by the equipment makers. Some of the design concept research is also being done by design EDA suppliers and others, or companies that do architectural designs like ARM and others. And then there is a whole new concept of, what do we design How do you just design and then get it made by somebody else? So there's a process and a technology platform research that needs to be done by a foundry, and they have to develop the platform and give it to someone like a Qualcomm or an Apple or an NVIDIA, who has to come through with their architectures and make sure that works very well. So they have device design to circuit design to architectural designs that have to come through on a given platform technology. So it's a very different world. So the need for public-private partnerships is still intact, especially given the fact that now the system makers have more of a sway. In the past, it was less of a sway from the system makers. You essentially had a chip that enabled a system to do much more. Whereas today, the system makers are saying, I want this functionality and this differentiation in my system. I'm going to make, I'm going to make this new ADAS system. And I need all these different chips and functionalities in there. So what can I get off the shelf versus what do I need to get made?
So if I'm going to reinterpret what you said here, historically it was a lot more vertical integration.
That's correct.
And now it's a distributed ecosystem that has a lot more players playing in smaller spaces, but very focused in those smaller spaces. So a public-private partnership still has a major benefit because you can pool from a lot larger source. It's just a restructuring of maybe the financial engagement model for the public-private partnership. So the utility is still there. Right. It hasn't been abandoned. It's just a reformulation of how to engage with those partners, correct?
Absolutely. I think the problem set has grown much bigger. And so what that does is you need super specialization in each of those areas to get the best out. So then you do need a public-private partnership that has these focal areas to say, okay, now we may have to accelerate in this specific area to make something happen. But system players are also playing a dominant role now. So it's actually exciting in many ways. Whether it's AI or it's 5G going to 6G and whatnot, or a whole range of other technologies. One other thing is that's waiting to happen is all the impact on life sciences that could come up. So it's a huge opportunity there. So if you just look at all these business verticals and what role microelectronics and semiconductors play, public-private partnership is still a very, very apt way to go about it. And I would say that we probably need more of those partnerships and more of those enabling engines that help startups and ideas, that come through the system to reach a certain stage of maturity and fruition before people can decide, is it worth moving forward or not?
Well, and we can't ignore the fact that microelectronics is a foundational technology.
Absolutely.
You don't have hypersonics without microelectronics, but you can have microelectronics without hypersonics.
That's right.
So, and that applies across the board for all other technologies. The utility is just so high that it is something that, every growth in technology is going to require the integration of current and future microelectronics.
Right. In fact, what is interesting, Dan, is that it's not only a requirement, but it could also be the differentiator in many cases. Let's take your example of hypersonics that you talked about. Well, a hypersonic, missile or a hypersonic plane or whatever it might be, requires some base electronics for it to be managed and controlled remotely or so. But if you wanted high degree of maneuverability, or if you wanted a high degree of anti-jamming properties, or if you wanted it to navigate where there is a GPS denial, for example, so those are all electronics driven. And if you wanted to add some of these features, or if you wanted to add features like, for example, stealth mode, some part of it comes from the physical design of how this craft is designed, but other part of it comes because it is actively jamming signals that are trying to intercept it. Right. Yeah. So these are all electronic driven.
And by the way, has to be reliable for these different types of applications.
Absolutely.
Now there's a shake and vibe aspect to it, which you wouldn't really have with a laptop.
Correct.
You have a spectrum of thermal instances, right, especially if it gets supersonic and the hypersonic hits a certain temperature variation that impacts. I mean, they might have shielding for the material on the front, but how is that affecting all of the base electronics that are allowing these a variety of things to happen? So yeah, that's interesting. So after your time over at Sematech, you went over to Intermolecular, correct?
That's right. I absolutely. Intermolecular was an interesting company because it had this phenomenal concept of combinatorial R&D acceleration concepts. And so that was really mind-bending, and we thought, okay, this could be something big for the industry itself. And the company came up with some really remarkable tools where you could segment a wafer into 200 plus coupons, or without really breaking the wafer, you could do 200 plus experiments on a given wafer. And it really accelerated some DRAM development activity, some logic areas, and some wet cleaning solutions and concepts and chemistries that were needed for that. So it was an exciting thing. And it was also a segue from what I was doing in Sematech in many ways. In Sematech, we were also looking at how do we accelerate these R&D concepts, because it is getting more and more expensive. The wafer size is getting bigger, which means you're spending more money on each wafer, but you can't really carcass a wafer and then say, I'm going to go cut it up and then see it. You get one data point or a certain set of data points from one wafer when you break it, but you also spend much more money in getting that data versus, let's say, a 4-inch wafer. And so how do you increase the efficiency of your R&D and with less dollars? And this is a constant challenge. So I probably should touch upon some things that happened at Sematech, which actually also helped me to make some of these moves. One of the things that I was trying to do at Sematech was I looked at how the industry was moving. And when I joined, Sematech was largely a group of companies and partners that were coming from the chip making club. So chip makers were all working together.
From the fabs?
From the fabs. They all had fabs. And then it struck me that this whole fabless community is growing very fast. And we do need to have them at the table. They may not necessarily benefit from the exact kind of things that we do, but we do need to have them at the table for a meaningful discussion. And the second piece that also struck me was that the equipment suppliers are doing more and more. And it is not completely common to have the equipment suppliers go and do materials and process development work turnkey that would be given along with the tool. But it was getting there, that they were developing things on their own. And they always needed electrical data for some of the processes they're doing, which they couldn't get by themselves. So you need to have them also in the fold to get a much better and meaningful discussion going. So I took it upon myself to go to the board along with our CEO and others. And we worked really hard to recruit these companies, as well as convince the board that there is a good opportunity in bringing them to the fold. So as we brought them to the fold, you could see the complexity that every one of them is dealing with. And if there was a better way or a simpler way of handling all these complex problems ahead of time, you would be saving time, you would be saving money. And so I said, intermolecular, the concept of what intermolecular was driving was quite interesting. So that's one of the reasons why I went there.
Yeah, it's an interesting role that intermolecular played in kind of the semiconductor ecosystem. But I want to, kind of fast forward a little bit. I know that you spent quite some time over at Zeiss, and that's when our paths, once again crossed. And interesting because, most people think of Zeiss as, optics and things of that nature, where you were helping to grow out and expand their semiconductor space. Why don't we touch on that real quickly before we get to the next?
No, Zeiss is a phenomenal company. I mean, like IBM, they have a lot of technical depth. And it was not uncommon to see people working on a given project for 15 years or 10 years and plus. And they were really proud of what they were doing. And it's even to date, I mean, I remember walking the halls of IBM and then meeting the world's expert on TEM or SIMS or DRAM. Bob Dennard was my neighbor. And, people like this were they're leaders in the field. And same thing happens when you go to Zeiss. Zeiss also has people who knew exactly how to polish these lenses down to perfection. And this is just art almost. I mean, it's not even science at some point. What Zeiss wanted to do was they had people working on electron beam, ion beam, X-ray optics, and a bunch of other technologies, which never really, they didn't really go out into the market as much. Although they were working on these technologies, they had developed some of these concepts. So they wanted me to come on board to help try to take this to the semiconductor industry and see how we could help the semiconductor industry with solutions that were not there at that point in time.
Interesting. Yeah, and for those that are viewing here, when Raj is talking about TEM and SIMS, these are all metrology things, measurements associated with very specific types of items that you're looking for. TEM, transmission electron microscope, for example. SIMS, I mean, there's different types of SIMS. There's time of flight SIMS. There's all the, I guess, basics of this is that instead of looking like through a microscope like you would in high school or something like that, looking at biology items, this gives you high resolution in specific areas, whether it be at the micron level, the nanometer level, or somewhere in between. The part that I kind of really interested in picking your brain on is at or around when you're at Zeiss, all of the buzz of this brand new U.S. initiative starts coming forward. We are going to revolutionize the domestic semiconductor manufacturing capability. And within this, there's going to be multiple segments associated with it. There's the CHIPS initiative that is being put forward. And one of the key areas that you played a role in and continue to play a role in is the R&D ecosystem, known as Section 9906 of the CHIPS Initiative, about $11 billion that is appropriated for this. And an opportunity comes up with Miter Ingenuity for you to, pave the way for the United States to have a foundation to build off of in this space. In concert with that, you also get tapped to go into the Industry Advisory Committee by the Department of Commerce to help as a visionary for how they can roll out this big plan. Why don't you talk a little bit about both of those?
I was one of the 24 people who were selected for the Industrial Advisory Committee. There are a lot of other people who are on this committee who are really smart people, very, very knowledgeable people who have tremendous experience. And so I'm lucky to be working with them.
You were the first group, right?
That's right. I was part of the first group, and then my role was extended. So that's what I'm still serving on that committee. But it was interesting that the whole concept of what we need to do in the country for semiconductors and manufacturing of these semiconductors started off in, I think, the NDAA. It was a Defense Appropriations Act.
Yeah, the Authorization Act, the National Defense Authorization Act. Yep.
Thank you. That came about in the previous administration of Trump, and that was really, it paved the path, and it sort of lit everybody's imagination with this whole concept of National Semiconductor Technology Center for doing R&D, coordinating all the R&D that we need to do in the country. And we also had to point out that by that time, Sematech was no longer in existence, right? So we needed a new, up-to-date public-private partnership entity that would drive this agenda. So when I was tapped to and asked to help with bringing everybody together, having a dialogue on what would that look like, what should it do, what should it not do, and how should it help the industry, it is an exciting opportunity. I mean, given what my background was, I said, this is something I should contribute to. This is my time to give back. And given that I have really benefited from the largest of the U.S. taxpayer, I said, this is my opportunity to give back. And so I joined that activity and the discussion. And I think we authored a few papers, position papers that were well received by the industry, by the Commerce Department and others. And so that really helped to shape everyone's thinking.
Yeah, it was a real good guiding function. I think that the national interest was there. And there was a lot of the supplier base that was, I mean, of course, you have $11 billion. Who's not going to be interested in tapping into that? But the big gap in between was, how do we get from congressionally appropriated dollars to ensuring that there's a framework that doesn't, repeat the same problems that we've, uncovered in the past, ensure that we're able to continue on with a focused and driven path forward that does accelerate things. And 3, buy down the risk from all of these different stakeholders playing a role. I remember we had numerous discussions about things like IP protection.
Correct.
How do you have two competitors that might be working on the same program not lose their crown jewels if they're trying to contribute back into this ecosystem. So all of these items, and that's just a sampling of a variety of different things. Right.
We were looking at a sort of a comprehensive set of issues, and I had a great team that was actually contributing to all this and making it happen. And then we had about 100 plus companies and entities, universities and R&D institutions and individuals that are from the industry with a lot of experience that came together every week for a 90-minute discussion to contribute towards it. So we broke things down into chunks, and we were trying to address one by one. It was a really good exercise that brought everyone to think on these concepts, but also to set up that framework, like you correctly pointed out, that taps into, well, how should we, or how best should we spend the money that was initially appropriated for this activity, the 11 billion or so, but more so, what would we do to sustain it in the long run? How would we ensure that there is value creation, both for the companies that were going to participate and also for the government and the country itself? And without the value creation, you just simply can't keep giving money, and you can't keep putting money from the government side or taxpayer dollars into that. So I think that was a great discussion, because I think the importance of semiconductors for national economies, national defense is very clear on everyone, especially after COVID. I mean, and I think that discussion centered around how do we ensure that sustainability angle is taken care of, along with what should we do? How do we leapfrog the current weaknesses that we see in the country, and how do we leapfrog from those weaknesses to a point of leadership? And packaging is one of those areas which we discussed quite extensively. What should we be doing as a nation to make sure that packaging is back on in our country? How do we provide a milieu for companies to come and extract more value from the ecosystem within the country, so that they would actually manufacture more of the chips in the US?
And one of the things that was extremely impressive, at least from my observation of all of the work that was being done, is you helped to co-author a what I would kind of summarize as the blueprint on how to do this. Many people love to pontificate on the idea, hey, we're going to build out this R&D ecosystem. We need to do this. And it really play on the technology seduction angle that most people have. And when I say technology seduction, it's the same thing that gets people excited when the new iPhone comes out, right? Don't know why they need to have it, but there will be a line that wraps around 2-3 buildings just to get access to it. So people love a new technology. So you have that. You have all of these people that want to play a role, but it's all kind of one-off 30-second discussions. You were able to create this, and I'll use the word blueprint kind of document that says, okay, here's what we're actually trying to do. Here's the lessons learned that we've had in the past, and here's a way for us to ensure that we're not going to go down a direction that could just be fraught with a lot of problems. And I think that foundational document that you put together, I don't remember the specific title. We'll have to put it in the show notes. But I think that is one of the reasons why you look at the ecosystem of the CHIPS initiative, why the 9906 section continues to move forward, where you've seen some pretty big setbacks in section 9902, which was supposed to be the crown jewels of that initiative, right? So I think that, if you want to talk to that, document a little bit, that would be good.
Sure. I mean, our idea was, how do you build something that is an enduring infrastructural contribution to the country, right? It's something that basically endures. With that concept in the backdrop, with that in your mind, you sit down and then you say, okay, what are all the things that need to be done? And how would you design something like that? How would you operate something like that? How would you govern it? And what kind of checks and balances do you provide? So this is an exercise in trying to convert some of those ideas and thoughts, or wishes, if you will, into concepts and actionable plans. So I think we did a good job. It was a collection of all these companies and entities that came together to make this happen. But it is exciting from that perspective, in the sense that everybody was focused on making sure that this was going to be successful in the right way. And you're right, the research part of it is, it's obvious to everyone who is in the industry that the 9906 part of it is critical for the betterment of the nation as we look into the future with microelectronics being everywhere now, right? So that part is moving forward, and I think there's a lot of good work that's happening right now in NatCast as they call it now, and the NSTC that is going to be the center around it. So there is research programs that are being released by them. There is also activity focused around discussions that are focused around what should be done in addition, and what additional topics should be done. Infrastructural build out, what would be a facility that is going to drive the future of these R&D activities in the country, and how do you help them to go from lab to fab by helping with piloting, both in front end device areas as well as in packaging. So there's a lot of work that is happening in the background. So it's quite exciting.
Well, and I think you touched on one of the critical pieces that gets ignored, ensuring that it gets to production, that there is a pathway to this. Mm-hmm. It doesn't just turn into some kind of hobby shop item that stays in a laboratory that may have good performance for, a peer-reviewed paper or something like that. The whole intent of this is to make sure that we do influence production down the road. We minimize those 10 additional minutes, those 6 additional minutes, whatever it may be in overall fabrication time. And those lessons learned are critical for this. So continuing your role with, the IAC, you've decided to then once again pivot over to being the president of IMEC US. And that is an interesting role because I'd say it seemed like day one, there was announcements that were coming out on established partnerships with, people over in Indiana, over in Florida. There was a period of time where it seemed like it was almost every week that there was a new announcement coming up, but they were focused in logical areas that made sense where IMEC and said location could contribute in a partnership that would thrive. So talk a little bit about your time over with IMEC.
No, and IMEC is an excellent R&D entity. In fact, I would say it is a leading entity that contributes to moving the industry forward today. And some of the work that they do at IMEC in Belgium is phenomenal. And the idea was, how do you extend some of that R&D activity to the US? How would you partner with local universities as well as research entities that might be in the US? And many companies in the US are already partners with IMEC. So when we came about thinking through this, we said, okay, let's partner with specific universities or specific locations where there may be interest in a specific topic, or maybe there is already a certain established excellence in those topics and interest in those topics. So we picked multiple states that were expressing interest in those specific topics, and we started driving partnerships. In Indiana with Purdue University, we were looking at 2D materials and what comes beyond. For logic technologies, similarly in packaging area, it was in Florida. There was already a facility that the Osceola County had pioneered well ahead, which is very thoughtful and very, I think, foresighted of them to have kicked off even before packaging became very popular. And that is a bold investment from them. And similarly with MIT, I think it was just recently announced, we were looking at life sciences. How do we partner together to drive some new concepts and new ideas and capabilities and breakthroughs in life sciences? And with Michigan in automotive technology. So we were driving themes. And to me, it was absolutely critical that we had specific themes in each location. And how do you bring all these different themes to help each other out? For example, automotives require new concepts in packaging and new solutions in packaging. So the team in Florida is working on general concepts of packaging, but whenever there is a new problem that comes from automotive sector, they could help. They are the experts in that area. And the drive and the directionality that each of those other units would provide to any one of them would essentially be very symbiotic. Are there new trends coming up in automotive packaging, for example? Are we looking at them? And so should the team in Florida start thinking more about them? Or, are there new requirements in medical technologies that need to be looked at, life sciences, and in terms of how fast the device works, or in terms of other aspects like in packaging again, you could be initiating that research in Florida and then feeding the other groups that are out there.
My understanding of kind of the way that you framed, each of these different partnerships is IMEC being the premier R&D hub in the world
Mm-hmm.
for research in semiconductors would act almost as the hub. And each of these locations would be spokes that you would
Mm-hmm.
connect into. So that way there was a two-part leverage that could happen.
Right.
In the instance of, let's say, Florida, for example, the packaging stuff there had maybe its own specific roadmap, its own specific tools, capabilities, et cetera, but it would plug back into the hub. So that way there would be a value add on both sides. It would expand with low risk on the IMEC side to explore new areas, but at the same time, tap back into the mothership here and be able to say, okay, look, here are some of the challenging questions we're facing, or resources that expand beyond ours that you guys over at IMEC could have. Do I have this kind of right?
No, you're right. You're absolutely. In fact, they were very complementary to what was being done in the mothership in Belgium, right? So in Belgium, we had certain capabilities. We had fabs, and we had labs that were doing some specific activities that would further the knowledge in that field. But often enough, you would run into situations where you needed something done much faster. Let's take 2D as an example. 2D materials, we needed something that could be synthesized, or it could be evaluated much more rapidly than in a 300 millimeter line, which has a lot of controls to ensure that what you get out is not garbage. So that could be done in Purdue research facility. They have a fantastic nanofab in Purdue, Burke Nano Center, where you could turn things much faster than you could ever do in Leuven. So any initial information that you would get from there would actually speed up the process that could be done on 300 millimeters. And that would benefit all the partners in turn. Similarly, in packaging, there were areas like RF and other areas that we were interested in that were being done in Florida. That is a focal topic. But a Florida facility also had a packaging unit that was attached to it that was being run by Skywater. So we could tap into that facility, and that would augment what we were doing back in Leuven. So there was very symbiotic, as I mentioned before, very symbiotic relationship between all these different programs, the different entities, and very complementary capabilities that would add on to the whole overall picture of what we could be doing. And by doing so, you had an ability now to not just, you're not trying to duplicate what was being done in Leuven, but you're actually trying to augment, and you're trying to further the knowledge, further the R&D activities so that things could be speeded up.
Yeah, so like a sculptor would add pieces of clay to the base piece, right? Each piece that you're adding here in these partnerships is helping to create, this beautiful image of what the future could be.
That's a good analogy. Yeah. Absolutely.
So now, I guess, with all of this R&D that is happening and the emphasis that the world has put in microelectronics, understanding that if you're not leading or investing in microelectronics, then you're jeopardizing not only your economic footprint, potentially national security footprint, a variety of different things, right? And you see this all across the world. We talked about Japan at the very beginning,
right?
But the Japanese continue to make investments. You hear about the Chinese, speeding up their investments and finding new and novel ways to do things like EUV lithography on their own nickel without having to rely on ASML and others to do this. The Europeans, India, there is notice that has gone out around the world that if you're not pushing in this space, then you are going to fall behind very quickly. Where do you see the future of R&D and the big next step? Do you believe that it's going to be something that is foundational in a public-private partnership? Do you believe that it is going to take a coalition of the willing from a variety of different countries? Or do you think that it's going to be industry pushed? For example, some of the big names like NVIDIA, for example, helping to drive and highlight their core focus. How do you see this evolution happening?
The importance of and the prevalence of microelectronics in everything that we do is unquestioned now. It's everywhere, and it's only increasing. So in some sense, some statistics basically point out that the industry is 600 billion today, roughly, and it's expected to grow to about $1 trillion by 2031, 32 timeframe, or even just before that. So while the industry that is just the semiconductor industry directly growing is growing to about $1 trillion, the impact that it produces on the world economy, it's tenfold or even higher. So, the whole where semiconductors go and how they enable a whole host of other industries is very important to note. So keeping that in mind, there is room for a lot of people to essentially do exactly what you said. How do we engender and how do we grow our own local industry? And how do we contribute to this bigger ecosystem that is coming up? And that's what the effort is right now everywhere. It's impossible for everyone to say, I'm going to be the leader in this field and I'm just going to go and spend a ton of money. There is going to be, as it is, as you see today, there are pockets of excellence around the world. And these pockets contribute to the bigger fabric of the 600 billion industry, which is growing fast. The reason why it is growing so fast is because of this supply chain dynamics that are so intricately woven across the globe. And from time to time, we have questions about whether that is safe enough or not. And do we need resilience in that system? And that's understandable. And that's a good question to have. But resilience only means that you have additional sources of these capabilities and part suppliers and others. So it means that there are more public-private partnerships that are necessary around the world. And those who are willing and coalition of the willing and coalition of like-minded allies should come together in those partnerships to see how do we break a problem down and how do we essentially go contribute. There'll be some overlap for sure, but overlap is not necessarily a bad thing. It revalidates some of the information that we learn, because validation is a very critical component of what we do in this field. In addition to that, by the fact that different regions have different focal areas of interest, you will see excellence in some of those topics. And we haven't really seen some of the new emerging areas that are going to be impacting this field. So different parts of the world might naturally gravitate towards some of those areas, and you will see more emphasis in those areas from them. So yes, there is a need for a lot more public-private partnerships, especially with regards to doing some of the basic research, making sure that some of these concepts are tested out fast, and then those concepts are converted from lab proof point to fab proof point. And even within that fab proof point, there are different kinds of fabs that are necessary. Initial stages, you might be okay with a university fab or a lab, if you will, but that needs to go into something more rigorous that can actually prove these concepts and then say, okay, the pieces are all coming together. What happens now is I have all the processes, I have all the materials. I need to be able to put them together to see if the promise is still there.
That's an interesting piece.
So that is a second type of a fab. In the R&D space, you still are not manufacturing. So you need those more rigorous fabs. Now a foundry looks at this and says, yes, I think I can take the risk of going and manufacturing the technology for this company. So you just think about this. What used to be done before in one simple fab is now being split across multiple fabs before it goes to production. So there is a lot of need for all this.
And there's a paradigm shift that you're underlying here with what you described. Let's take, for example, it's going to take a two-part piece, right? An academic manufacturing facility, a Purdue, for example, may need to break down the wall that they have, that this is a research-focused type of thing with a pathway more leaning towards integration into full fab, where an Intel, for example, which is usually rather isolated from allowing others to influence, their manufacturing process, may need to break down that wall as well. So if we can break down both of those walls, it might create a larger synergy to enhance a more robust integration of R&D into fabrication. Did I kind of capture that?
You're right in the sense. I don't see that as breaking down any walls, because each one of them has their own constraints. Like Intel, for example, would not want to put something that's not well tested into their fab, right? So they wouldn't break the wall down, but they would have some criteria to say, okay, you need to pass through these gates before I feel comfortable enough to put it into my multi-billion-dollar fab and bring it into production. Similarly, when a Purdue or a Michigan or any other lab or a facility, nanofab facility that does this work, wants to make a technology come to life, it's not just proving one device. Now they also understand that repeatability is important. But how do you do it fast enough in their facilities, but with certain degree of repeatability, certain degree of criteria that would benefit the next stage at an IMEC or at the NSTC facility in future, to say, yes, that looks promising. So therefore, we are going to put it into this R&D facility now and test it out and make it even more robust and make sure that it is actually manufacturable. Because let's say you have a new 2D material. Having a new 2D material and trying to make it work in a lab is one thing, and even in a small fab. But now the question becomes, okay, how are we going to put this 2D material on a full 300 millimeter wafer? What techniques are we going to use to etch? What techniques are we going to use to measure things on this? And how do we prevent any contamination that may come from this? How do we ensure that at the end, when you finish this device, that the right contacting scheme is applied and the right packaging technologies are applied? What is the design environment for this? So there are a lot of questions that are necessary to be answered before the technology is even sort of proven for an Intel to pick up, right? And the benefit is that we have the Intel and the NVIDIA and others giving guidance saying that, okay, we are making our product and we are busy doing what we are supposed to do. But guys, that is what you need to check. Don't forget about this other distraction. You actually want to focus on these topics. So their guidance is really valuable in making these technologies come to life.
Well, Raj, this is it's been a great discussion. I really appreciate you taking the time here, being on the podcast, and looking forward to continuing to track the influence that you make in not only the semiconductor space, but a lot of the investments that are happening worldwide. So really appreciate you coming here on the and taking the time.
Thank you for having me, Dan. It has been a pleasure. And as always, great discussion with you. Thank you so much.